Welcome to the course on error control coding and introduction to convolutional codes. So, we will start with introduction of convolutional code, and today we are going to discuss how we can encode an information sequence using convolutional code. So, today's topic of discussion is encoding of convolutional code, and we will take a very simple example of a rate 1 by n convolutional code. As you know, a convolutional code processes information sequence in a continuous fashion. So, information bits come in and we can get continuous output from a convolutional encoder. We also know that the output of a convolutional encoder depends not only on the current input, but it also depends on past inputs and past outputs depending upon the memory of the convolutional encoder. And as we have seen, we can realize a convolutional code using shift registers. So, we describe a convolutional code basically as an nk convolutional code with memory m. Now, as we have said before, as opposed to block codes, typically the value of n and k for a convolutional code is much smaller, like k may be 1, 2, 3, and similarly n will be maybe 2, 3, 4, like that. So, this is one example of a memory 2 convolutional encoder. We can see this is our input u of l and output v of L1 and v of L2. Now, note that the output VL1 and VL2 depends not only on the current input, but also depends on the past inputs as indicated by content here and content here. And this is k equal to 1 because there is only one input here, that is why k is 1. There are two output, this one and this one, so that is why n is 2, and since the output depends on two memory elements, this and this, m is 2. So, this is a 2-1-2 convolutional code. So, as we said, the input is u of l and the output is v of L1 and v of L2. And how is v of L1 and v of L2 depend on ul and the past values? This is given by the interconnection. So, we can see for VL1 it depends on input ul as given by this, and it depends on ul minus 2 as given by this link. So, VL1 is given by ul and ul minus 2. So, it depends on the current input and the input which was there 2 time instance earlier. Similarly, VL12 depends on ul as given by this interconnection, ul minus 1 as given by this interconnection, and ul minus 2 as given by this interconnection. So, this is our VL2. So, these are the two outputs and this is how they are related to the input. So, we can see that whether a particular input appears in the output, that is basically given by these interconnections. These interconnections tells us whether that particular bit is taking part in the output or not. So, if we denote by nu I the length of the ith shift register in a convolution encoder, then we define the memory order as the maximum length of the shift register among the k shift registers used to represent the convolutional encoder. And this parameter m is also known as memory order of the convolutional code. As we know, this ratio of information bits to coded bits k by n is known as code rate, which we denote by capital R, and the overall constraint length is defined as sum of length of all the k shift registers. That is the overall constraint length. Now, we are going to show how we can encode a convolutional or information sequence using a rate 1 by n convolutional encoder. So, since it is a rate 1 by n convolutional code, so k is 1, n number of coded bits is n. So, there is one input coming in and there are n outputs, and the maximum length of this one shift register used to represent this rate 1 by n code is m. So, this shift register has m memory elements. So, let us take our input which we denote by u to be u0, u1, u2, ul minus 1. Since it is a rate 1 by n convolutional code, so what we would get is corresponding to one input we are going to get n outputs, and we denote these n outputs by v1, v2, v3, vn, where each of these vi's can be written like this. So, the output at a particular instance then is, so corresponding to u0 then what is the output? These are the n bits output corresponding to this input u0. Similarly, corresponding to u1 my output is this, corresponding to ul my output is this, it's n bit output. Okay. So, I write the output by v0, v1, v2, vl, where this vl is an n bit vector. Now, how do we generate these n bit vector from this one input? And if you just go back to our example that we had shown, look at this example. How did we generate two coded bits corresponds to one information sequence? How did we generate these two coded bits? These coded bits were generated by various combination of input and these parse inputs, and whether a particular bit appears in the output, that is governed by these interconnections. Whether there is a line connecting this part to the output or not, that determines whether that particular bit is participating in the output bit. So, what we can conclude from here is basically we can completely specify a code by this set of n generator sequence of length m plus 1, where each of these generator sequence is basically of length m plus 1, and what are these g01, g11, g12, gm1. So, you can see, so this superscript that you see 1, 2, 3 and n, this corresponds to each of the output sequence. So, the first output sequence is specified by this generator sequence G1. The second output sequence is specified by this generator sequence G2, and the nth output sequence is specified by this output sequence Gn. And what are these Gi's? Now, note that the memory order of our convolutional encoder is m. So, there are, so if let us say, just take an example, m equal to 2. So, if we take m equal to 2, let us say 2 memory order. So, then basically, and this say this is my input ul, and my output I can take from some interconnections from this. Let us say this is my example that I had. This was my VL1, this was my VL2. Now, note that these interconnections are specifying whether a particular bit is participating in the output code sequence or not. So, if we look at the first coded bit UL, now this has memory order m. So, there are possible m plus 1 connection. What are those possible m plus 1 connection? First one is corresponding to whether UL is participating in the output bit or not. Second one corresponding to whether UL minus 1 is participating or not, this is this point. Third one is this point, whether UL minus 2 is participating or not. Similarly, the second coded sequence, whether UL is participating or not, whether UL minus 1 participating or not, whether UL minus 2 is participating or not. So, we can see that the output here, let us take the first output sequence, that is completely specified by whether UL is participating, where UL minus 1 is participating, and whether UL minus 2 is participating. So, in this example G01, G11 and G2m completely specifies what inputs are participating in generating our code sequence. Similarly, look at the second bit. Here also these m plus 1 connections will completely specify whether a particular bit or the pass bits are taking part in the output coded bit. So, you can see if you have a rate 1 by n code whose memory is m, then we can completely specify that code using a set of n generator sequence, where each of these n generator sequence correspond to one of the output sequence, and each of the generator sequence is of length m plus 1, specifying the interconnections of UL minus 1, UL minus 2 up to UL minus m. So, then what are these G01 and G11? If G01 and G11 are either 1 or 0, 1 means they are participating, 0 means it does not participate. For example, in this example, what is G11? Is UL participating in the output sequence of VL? Yes, it is. So, then G01 will be 1. Is UL minus 1 participating in the output sequence VL? No. So, then this will be 0. What about UL minus 2? It is participating in the output sequence, so it will be 1. So, G1 is 1 0 1. Similarly, G2 will be 1 1 1, because UL minus 1 and UL minus 2, they are all participating in the output coded sequence. Okay. So, if I specify these generator sequence, then my convolutional code is completely specified. And what is my output then? My output is nothing but it is a discrete convolution of the information sequence with this generator sequence. So, if my generator sequence, if my code has memory m, then basically I can write this discrete convolution in this particular fashion, and that is basically my output sequence, which is discrete convolution of the input sequence with this generator sequence. Now, let us take an example. This is the same example that we are considering. This is a rate 1/2 code with memory 2. So, you can see V1L, this is basically again discrete convolution of input with this generator sequence, which we can write as UL plus UL minus 2, and this V12 can be written as UL plus UL minus 1 plus UL minus 2. If we go back, our output is this. If we can expand it for this particular example, this will be UL G0 I plus UL minus 1 UL minus 1 G1 I plus UL minus 2 G2 I. And for the first coded sequence, this G0, G1, G2 was 1, 0, 1, and the second sequence was 1, 1, 1. That's why the first coded sequence is UL plus UL minus 2, and the second coded sequence is UL plus UL minus 1 plus UL minus 2. So if we have an information sequence this, what was our output sequence? We had VL1 is UL plus UL minus 2 and VL2 is UL plus UL minus 1 plus UL minus 2. Now, we can show that our output coded sequence will be given by this. Now, this can be easily verified. So, let us say what was our output coded sequence? VL was UL plus UL minus 2 and VL2 is UL plus UL minus 1 plus UL minus 2. Now, note when the first input UL, which is 1, comes, what is the output? Now, to specify the output, we need to specify what were the initial contents of UL minus 1 and UL minus 2. So, initially we will assume that the convolutional encoder was in all 0 state. Now, what do we mean by all 0 state? So, we are assuming that initially the contents of the shift registers were all 0. In other words, UL minus 2 and UL minus 1, they were both 0. Okay. Now, if both were 0 initially and if UL is 1, what will be VL1? This is 1 plus 0, which is 1. So, you can see this is 1. And what is VL2? This is 1 plus 0 plus 0. So, that is also 1. Next, what happens? Next, if you go back, this 1 which was here, when you apply a clock, this 1 moves here and a new bit comes here. So, now in the next time instance, UL minus 1 becomes 1, and what is UL minus 2? Since UL minus 1 initially was 0, so this 0 will come here. So, the new contents of the shift register will be now 1 and 0. So, what we have is now UL minus 1 is 1 and UL minus 2 is 0. Now, the next input is 0. So, next input is 0. So, what is the next output? This is 0 and UL minus 2 is 0. So, this will be 0. You can see this is 0. What about this? Now, UL is 0, UL minus 1 is 1 and UL minus 2 is 0. So, 0 plus 1 plus 0, that will be 1, and that is given by this. Okay. Next, what happens? Again, go back to this diagram. You had an input 0 here. So, now this 0 will move here and you had a 1 here. So, this 1 will move here. So, the new contents of the shift register will be 0 and 1. Okay. If that happens, then next input is 1. So, if this is 1, what is UL minus 2? UL minus 2 was 1. So, 1 plus 1, that is 0, and UL is 1, UL minus 2 is 1 and UL minus 1 is 0. So, 1 plus 0 plus 1, that is 0. So, like that you can basically write down the output coded sequence. So, then what is my final output? So, corresponding to this 1, then what is my coded sequence? That is given by this. Corresponding to this 0, my coded sequence is given by this. Okay. So, then I can write my final output as, so corresponding to input 1, I get 1 1, that is given by this. Corresponding to 0, I get 0 1, that is given by this. Corresponding to 1, I get 0 0, that is given by this. So, this is how I can write my output coded sequence. Now, the same thing I can write in a matrix form. So, I define this generator matrix G, which generate this code word. So, the output code word can be written as input times this generator matrix G, okay. And this generator matrix is of the form like this. So, let us just expand it and maybe try to explain why the generator form has this semi infinite kind of form for a convolutional code. So, let us say U is U0, U1, U2, it's continuing set of sequence like this, right. Now, what is your output sequence? Output sequence, so initially what happens? If you go back to this diagram, initially you are assuming that the encoder is in all 0 state, correct. So, what will be the first output that you will get here? That is nothing but U0 times G0. What is G0? G01 is this, G02 is this interconnection, which is connecting UI to the output. So, at first time instance, what you would get is the output is nothing but U0 times G0. This is the output that you will get at first time instance. What is the output that you will get in the second time instance? Now, whatever U0 you had, now that U0 has moved here, correct, and a new bit which is U1 has come here, U1. So, what is the output at this time? It is U1 times G0 plus U0 times G1. So, I can write in the second time instance my output is given by U1 times G0 plus U0 times G1, fine. Next time instance, what is my output? Again go back. Now, what is going to happen is this U1 will move here. So, this will be now U1, this will become U2 and this will become U0. So, what is my output now? It is U2 times G0 plus U1 times G1 plus U0 times G2. So, go back. So, what would be my output here? It is U2 times G0 plus U1 times G1 plus U0 times G2. What happens next? This U0 moves out. Here what we will get is U1. This will be U1. What about this? This will become U2. So, this is U2 and this will become U3. So, this is U3. So, what will be the output now? It is U3 times G0 plus U2 times G1 plus U1 times G2, and U0 does not appear because the memory order of this code was 2. So, what is the output in this case, third instance? This will be U3 times G0 plus U2 times G1 plus U1 times G2. Now, if we write the same thing in a matrix form, so what is V? V is basically V at time 0, time 1, time 2. If we write this in this particular form, is equal to U times this matrix G. Now, you compare this equation with this equation. So, at first time instance, our output is U0, G0. So, that is what? So, this is U0 times G0. So, this is G0. Second instance, what is my output? My output is U0 times G1, this term. U0 times G1 is this term, and then G0 times U1, which is this term. So, the second entry of this generator matrix is this. Okay. Now, what is this third entry here? You can see U0 times G2. So, U0 times this is G2 plus U1 times G1, that is this. So, this is G1, and then this is U2 times G0. So, you can see. Then further, if we look at this, what we get here is, so U0 times 0 will get here, and then we will get U1 times G2, U3 times, so this will be like 0, G0, G1 and G2. So in this case the memory order was M, that is why we are getting like this. So you can see here our generator matrix is of the form of semi-infinite form, where basically our G is something like this. So we have G0 to Gm, now this becomes 0, now this is new G0 and this is Gm, and then this is 0 0, this is G0. So it's like in this way diagonally my generator sequence is moving, and that is what I have written here. So if I try to write it in the form of generator matrix, then I can, my generator matrix in this case is a semi-infinite form, and through this example for a memory 2 code, we showed that this basically G is of the form like this. Okay. And where each of these G0s are basically these will represent what are these n bit output. So let us continue with the example that we are considering so far. So we are continuing with our rate 1/2 code whose memory order is 2, and we know our generator sequence for the first code sequence is given by 101, because my output VL is UL plus UL minus 2. Similarly, the generator sequence for the second code word is given by 11. Okay. Then can I write basically what is my G0, G1 and G2. So G0 is given by, now there are 2 outputs, so G0 will have 2 terms, the first term corresponding to the first coded sequence. So here this is 1, and what about the second coded sequence? That is 1. So G0 is 1 1, G1 is, this is 0, so this is 0 and this is 1, so G1 is 0 1, and what about G2? G2 is, this is 1 and this is 1, so G2 is 1 1. So I can then write my generator matrix, which is of the form, G is of the form G0, G1, G2, and the rest all of these are basically 0. These are 0, these are all 0. This is G0, G1, G2, and then these are all 0. So what is G0? G0 is 1 1, so that is what I have written here. G1 is 0 1, that is what I have written here, and G2 is 1 1. Rest all these entries are 0. Similarly, this is 0 0, and then I have G0, G1, G2, and then these are all zeros. Okay. So this is how I can write a generator matrix. Now let us verify our coded sequence that we calculated in the last time. Coded sequence corresponding to this information sequence was given by this. This was our coded sequence corresponding to this information sequence. Now, let us try using this generator matrix. So, if we use the generator matrix, then our first input is 1. So, 1 times G0, that is this. The next is input is 0. So, 1 times this plus 0 times 1 1, that will be 0 1. Next 1 0 1. So, 1 times 1 1, 0 times this, 1 time this. So, that is 0 0. So, we can see basically we are getting the same output sequence. We can just verify 1 1 0 1 0 0, 1 1 0 1 0 0. So, we are getting the same output sequence as before. Now, we are going to give you a polynomial representation of this generator sequence, which is very convenient in case of convolutional codes. So, I am introducing a delay operator D. So, if you have one memory element delay, that will be D. If you have delay of 2, it will be D square. If you have delay of 3, you have D cube. So, the exponent of D is going to specify how much delay. Okay. So, what I am going to show you is that I can write my output sequence in this polynomial notation as U times D into Gi times D. So, every output code sequence can be represented as product of this information sequence using this delay operator multiplied by this generator sequence in this delay operator framework. And the overall code sequence, when we have a rate 1 by n code, can be given by this expression. So, let us first try to write each of these terms in terms of this delay operator polynomial representation, and then we will show that this time domain representation, where we were computing the output using convolutional discrete convolution, can be similarly obtained using just this operation in the delay domain, which we are calling transform domain operation. So, we will take the same example that we were considering. So, I will just go back and show you again the convolutional encoder. So, this is the convolutional encoder that we are considering. We have one input, we have two outputs. Output depends on past two inputs. So, basically memory order is 2. G1 is given by this, G2 is given by this. These are my output V11, V12. These are my output sequences. Okay. So, let us look at this. So, G1 is 1 0 1. Now, what does this 1 corresponds to? 1 corresponds to this connection G0, which is linking my input UL. So, that would be UL without any delay. So, that would be 1. What was this? This corresponds to G1, that is input delayed by 1. So, this will be represented using D. So, D times 0 will be 0, and this will corresponds to G2 basically, and this is delay of 2. So, this will be represented using D square. So, this G1 in this transform domain using this delay operator can be written as 1 plus D square. Similarly, this G2, which is 1 1 1, can be written as 1 plus D square. So, this is my G2 of D. Now, the information sequence also I can write in this delay notation. This is U0, U1, U2, U3. So, this is the information sequence I am getting at this time. This after one delay element, 2, 3, 4. So, then this will be 1 plus D square plus D cube plus D4, and that is basically my information sequence. Now, the discrete convolution of information sequence, this G1, is basically given by this, and this if I write in delay operator form will be what? 1 plus D square D cube plus D4 D5 plus D6. And what is UD? UD is given by this, G1d is given by this. So, let us multiply these two. So, what do we get? So, if we multiply ud by G1 of d, so 1 times this will be 1 plus d square plus d cube plus d4 plus d square times 1 is d square, this will be d4, this will be d5 and this will be d6. So, d square plus d square is 0, d4 plus d4 is 0. So, what we are left with 1 plus d cube plus d5 plus d6. This is precisely what you get here. Okay. So, you can see basically these two in representation is equivalent. Similarly, we can write u2 which is given by this, and you can verify for yourself that u2d is given by this. Now, once you have these individual sequence, how do you write the overall output sequence? So, note that for one input sequence you are getting n outputs. Okay. So, this is taken care by this. So, if VID is going to give me output sequence corresponding to each of this outputs. Now, if I can combine this n outputs in this particular fashion. So, I take the first output, note that I have made a d to power n, because if it is a rate 1 by n code, the first output will appear after every n bits. The first bit is from the first coded sequence, then after n bits it will again repeat, it will come meaning. So, that is why I have made it dn. Now, how do I combine these n sequences? So, note this is output v1 dn is output from the first coded sequence, this is the output from the second coded sequence, that is delayed by 1, the output from third sequence will be delayed by d square, and similarly the output from the nth sequence will be delayed by n minus 1. Go back here. These are the two individual outputs. How are we getting the final output? So, note here, I am taking first bit from here, that is 1, second bit I am taking from here, that is this, the third bit is this, which is this, fourth bit is this, which is this. So, what am I doing? In this case, rate was 1/2. So, after you can see in the output, every second bit is coming from this. So, this is my 1 which is appearing here, this is my 0 which is this is my 0 which is this is my 1 which is appearing this. So, note this is appearing every second bit, and that is why what we did was, when we combined, we made it, each of this coded bit we made it d raised to power n. Next, if you look here, the first coded sequence is this one, this is the output from the first coded sequence, and what is the output from second sequence, which is this one. So, what are you doing when you are combining these output sequence, which is V1 and V2? So, you are taking V1 like as it is, only thing is it is spread out after every second bit, and V2 is delayed by 1 and it is also spread out. This is 1, this 1 is appearing here, this 0 is appearing here, this 0 is appearing here. So, every second bit is also from this encoded sequence, and note that this is delayed by 1 corresponding to V1. So, that is what we are doing here. If you combine this, consider this combined output sequence, there are n coded sequence V1, V2, V3, Vn. Now, first sequence we just take V1 d to power n, second is V2 d to power n, third is V3 d to power n, and then each one of them are delayed by 1. So, this is no delay, this is delay of 1, delay of 2, and this is delay of n minus 1. So, overall code sequence will be given by this expression. So, I hope I made it clear why this is d raised to power n and why each of the parity bits are delayed by 1 power like d, d square, d cube, dn minus 1. So, following this basically we can also write our encoding sequence in this particular form, where output sequence is given by u dn times gd, where gd is, this is a generator sequence from the first coded sequence, the generator sequence from the second delayed by 1, generator sequence of the third delayed by 2, generator sequence of the n delayed by dn. So, the overall encoding sequence can be equivalently written like this. And we can again go back to the same example. Our output sequence in a time domain was given by this, and if we follow the same procedure, v of d should be u of d square times gd, where gd is g1 d square plus d g2 d square. So, u d square is, what is ud? What is ud? Go back to the example. ud is 1 plus d square plus d cube plus d4. So, this is ud is 1 plus d square plus d cube plus d4. So, u d square will be 1 plus d4 plus d6 plus d8. So, that is what we have written here. Okay. And what is gd? gd is g of 1 d square plus d times g2 of d square. And what is g1 d and g2 d? g1 d is 1 plus d square, and this was 1 plus d square. So, g1 d square will be 1 plus d4, and this will be, so this will be 1 plus d4, 1 plus d4, and g2d will be g2d square. This is, so this term is given by this. Let me, I hope this is clear. So, g1d is given by this. What we are interested is g1 d square. So, g1 d square will be given by this expression, and we are interested in g2 d square. So, this will be given by 1 plus d square plus d4. Now, what is our overall gd? This is given by g1 d square plus d times g2 d square. So, then this will be g1 d square is 1 plus d4 plus d times this. Okay. So, this can be written as 1 plus d4 plus d cube plus d5. So, this is 1 plus d, this is 1, d cube, d4, d5, d5. Okay. So, this is our g of d. Now, if we multiply all of them, what we get is this, and we can write this. What is 1? 1 is 1, d is this, d square is 0, d cube is 1, d4 is 0, d5 is 0, d6 is 1, d7 is 0, d8 0, d9 1, d10 1, d11 0, d12 1, d13 1. So, this is our output sequence. Now, compare with this, what we got in time domain: 1 1 1 1, 0 1 0 1, 0 0 0 0, 1 0 1 0, 0 1 0 1. So, you can see basically we are getting the same sequence: 1 0 1 0, 1 1 1 1, and rest are all zeros. Here also we are getting all zeros. So, the point to take is these generator sequence that we wrote using this time domain representation, we can similarly represent them using this display domain representation, and it is lot more convenient to write it in this particular notation, because then the output sequence is just product of the input sequence and this generator sequence in this domain. So, with this I am going to conclude this lecture. I just want to make another point, that these generator matrix that we saw, for example, this G1 of D, which we wrote as 101, and G2 of D, which is 111, it is typically represented using octal notation. So, in many books, when they will describe the convolutional encoder for this, they will write it as 5-7 code, because octal notation of this is 5 and octal notation of this is 7. So, in many places they will say it is a rate 1/2 5-7 code, and what it means is they are specifying the generator sequence using this octal notation. Thank you.